Hello everyone, welcome to the last session of the root locus, and here we are going to discuss the rest of the two rules with the help of one example. So till now we have seen that how to plot the root locus, and for that we have also discussed few rules. So I'm going to take one example over here by which we will cover the rest of the two rules, and yes, the application of the rules which we have already discussed. So let's consider a feedback system with characteristic equation given value there. So this is the characteristic equation given to us for a particular feedback system, and here plot the root locus for the given where your day varies from 0 to infinite, and then we need to see that how your poles behaves on S plane. So we have already seen most of the rules to plot the root locus or to sketch the root locus. So we'll apply those rules also. And yes, at the end of the last session, we have also seen the two rules are related with the complex poles. So this is the same example which we have taken in the last class. At the end of the last class, here the poles are at 0, -3, and these two complex poles are placed at -1 plus minus j1. So when we have the two poles complex in nature, so we need to see that how they will leave from their open loop poles and then how they are going to travel in the S plane. So how they are going to leave from the open loop poles, so that is decided by some angle, at which angle they are going to leave. So this angle or the angle by which they are going to departure from their open loop poles is known as the departure angle. So let's keeping this in the mind, this particular characteristic equation, I'm going to plot the root locus. Let's draw the S-plane first, real axis, ABC axis, and now plot the open loop poles. For the given particular example, we don't have any physical zero given in the transfer function. So that means for the given example, we have four poles placed at 0, -3, and -1 plus minus. So we have four poles, and that means all the four loci are going to terminate at infinite, because all the four zeros are placed at infinite, because there is no physical zero given in the transfer function. Point out the open loop poles on the S-plane. One is at 0, the other one is at, let's say, -3 over here, and the two poles, complex poles, are placed at -1. Let's say if this is your -1 and this is plus j1 and this is minus j1. So the two poles are placed at -1 plus j and -1 minus j. Now, first rule to check the root locus on the real axis. So let's find out the root locus on the real axis. As we have already seen with respect to the rule, the root locus on the real axis, if right to the any point, the number of open loop poles and zeros are in odd number, so that part will be the root locus part. So if I'll consider all these points in this segment, and if I look to the right of all these points, I'll find out only one pole placed at 0. So right to this point only one pole, right to this point only one pole, so odd numbers of poles and zeros. So all these points up to here will be part of the root locus. So this segment is a part of the root locus, and if I'll just check one point on this segment over here after -3, and I'll look at to the right of this point, I have two poles placed at -3 and 0, so it makes it even number. So this point, neither this point or any point on these segments after -3 is not going to be part of the root locus. So now this is clear. On the real axis, this part is the root locus part, and this pole, let if these two poles are like this, so these two poles are traveling towards each other or converging towards each other. So now one thing is clear, we are going to have the breakaway point because two poles are converging towards each other. So let's find out the breakaway point. To find out the breakaway point, we need to see the equation which is dk by ds, and the root of that equation is nothing but the breakaway point. So now let's see. The characteristic equation was this: 1 plus k over s into s plus 3 and s squared plus 2s plus 2, and from is equals to 0. So this is your characteristic equation, and from here your k, or if I'll just further simplify it, this will become s into s plus 3 s squared plus 2s plus 2 plus k equals to 0. So this is the characteristic equation I have got from this relation, and from here your k will become equals to minus of s plus 3 and s squared plus 2s plus 2. So this is the k, and to find out the breakaway point I need to find out the dk by ds. So let's differentiate this equation with respect to s, and I'm directly giving you the relation, and this will be okay. Let's simplify this it further. So we'll have k is equals to s4 plus 5 s cubed plus 8 s squared plus 6s. So this is nothing but the simplification of this equation, and now let's differentiate it with respect to s. So dk by ds will be equals to 4s cubed plus a minus is over here. This is minus. So minus over here 4s cubed plus 15 square plus 16s plus 6, and we need to find out the root of the equation, and of course this is a third order equation. To find out the root is also difficult, but I'm directly giving you the roots of this equation. The one root of this equation is at minus 2.3, and the other roots are does not exist between 0 and minus 3. So we have three roots of this equation, from which one root exists on minus 2.3 and the other two roots are does not exist between the 0 and minus 3. So I'm not going to find out the other two roots. So this root or this point minus 2.3 is definitely going to be a breakaway point, because it is a part of the root locus, because it exists on the root locus segment on the real axis, and let's say 2.3 is somewhere here, so minus 2.3. So this is the breakaway point. So from here your root locus or these two loci are going to break away, and then they will go towards the infinite. And now here comes the next rule: if the loci are going towards the infinite, because all the zeros are placed at the infinite, so they will go along with asymptotic angles, and to find out the asymptotic angles we need to apply the next rule, and those angles will be drawn from some centroid point. So the next rule is to find out, or the next point is to find out the centroid and asymptotic angles. So now let's see this. To find out the centroid, I'm directly applying the centroid. For I have represented it sigma in the previous classes also. So sum of the real part of the poles. So one pole is at 0, other pole is at minus 3, and the remaining two poles are at minus 1 plus minus j, and the rule is just take the real part of the poles. So minus 1 is the real part of these two poles. So minus 1, and we don't have any 0, so that's it, divided by number of open loop poles minus number of open loop zeros. So we have 4 pole given in the transfer function, and we have 0 zeros, physical zeros, given in the transfer function. So n minus m will be 4, and the centroid from here will be minus 1.25. Now let's find out the asymptotic angles. Phi a, and the formula is 2q plus 1 into 180 degree divided by n minus m, and from here your q will vary from 0, 1, 2 and up to n minus m minus 1. So for the particular example, your n minus m is 4 and minus 1, which makes it 3. So your q will be vary from 0, 1, 2 and 3. So when we will put the q values 0, 1, 2 and 3, so we are going to have the 4 asymptotic angles. And it is pretty much clear because we have 4 open loop poles. So we'll have the 4 loci, and we don't have any physical 0 given in the transfer function. So all the 4 loci are going towards the infinite. So definitely we are going to have the 4 asymptotic angles, because all the 4 loci will go towards the infinite along with these 4 asymptotic angles. So let's put q is equals to 0. So your first asymptotic angle is 45 degree, because when q is equals to 0, 180 divided by 4, so it is 45. The other one is 135 degree when q is equals to 1. When q is equals to 2, it is 225 degree, and when q is equals to 3, it is 315 degree. So we have centroid at minus 1.25, and we have 4 asymptotic angles. So now let's draw this on S-plane. Again, I'm going to draw the S-plane over here. Poles placing 0, minus 3, minus 1, plus j, minus 1, minus j. This part is of root locus. Breakaway point is at somewhere here, minus 2.3, and centroid is at minus 1.25. So let's say this is your centroid, and from here I need to draw the 4 asymptotic angles: 45, 125, 225, and 315. So these are the 4 asymptotic angles, and by these two loci are converging towards each other, and they will break it from minus 2.3. So, and definitely they are going towards the infinite, so they will go towards the infinite along with these 2 asymptotic angles. So they are going towards the infinite. So now this is pretty much clear. These two poles, no matter what is the value of k, because here the poles values are 0 at a minus 3 when k was 0. As I have increased the value of k, this pole travels to the left, this pole travels to the right. They have converged at point minus 2.3. They break away from this point, and from this point they are going towards the infinite along with these two asymptotic angles. So no matter what value of the k, these two poles will always remain in the left side of the S plane. Now, what about these two poles? Now, two locus are clear. We have left with the to sketch the remaining two loci, and these two poles are also or will also go towards the infinite along with these asymptotic angles. So definitely they are going towards the infinite along with these two asymptotic angles, and definitely they are going to cross the imaginary axis, because if they have to go towards the infinite, they will go towards the infinite. They may go along with this asymptotic angles like this. They may go like this, and they may go like this also. So how we are going to decide they are going towards the infinite along with or parallel to this asymptotic angles? This is pretty much clear. But how they are going to leave it from here, at what angle, that can be determined by angle of departure. And the formula of angle of departure is, can we find out, 180 plus phi, and where phi is angle made by zeros minus angle made by poles to this pole. So what I'm going to do, I'll just take one arbitrary point near to this pole, complex pole, or you can just assume that you are drawing the phasor to this from every remaining poles and zeros. So let's draw it. One phasor is from this pole, other one is from this, and one is from minus 3.